All right, we are back and we are going to do our problem set 6 solutions. So which material is the stiffest? So that's going to be looking at our Young's modulus. So we can see probably, I would say the green. So this material here. Oh, actually, let me change my pen. And let's go ahead. So the green material, I would say the stiffest. Toughest, so remember, toughest is going to be the total area under the curve. So it's going to be hard to guess quantitatively, but I would say the red, most likely. So I'd say the red. Strongest is the largest ultimate tensile strength. So the ultimate tensile strength would be probably, I'd say this guy. Because it looks like, yeah, we're above. So that'll be the green as well. Highest yield strength, definitely the green as well. Ductile, the most ductile looks to be like the black. Most brittle, that would be, it's pretty close. So let's see, it's probably a tie between these two. So probably either pink or light green for most brittle. For the red curve, indicate quantitative values of the strain at failure. So strain at failure is probably this point, probably 0.32. Failure stress, that's going to be about 100 megapascals. Also ultimate tensile strength. What's my yield stress? Probably about 950 megapascals. What's my yield strain? That's probably going to be about this is 0.05, probably 0.01 approximately. All right, let's move on to number 2. So we have a mystery material here under this stress state. If it's a mystery material, then we don't know what's our Young's moduli. We don't know our Poisson's ratio either. So those are two unknowns. We have our coordinate system here. We're also told the red material is in a cube. We have the length here, rigid walls, and the shaded walls are physically attached to the material. Top of the cube is open. The temperature changes from room temperature, so my delta T is equal to 100 minus 25. So that's my delta T. I have my thermal expansion coefficient here. That's my alpha. The final length in the 2 direction, actually we're also told that the force applied here is 10 kilonewtons. What else? Final length in 2 direction is that. The final length in the 3 direction is that. So let's write out our stress and our strain tensors. So we're pushing in, basically, so we're pushing the material in here. We are increasing temperature, so the material should want to pop up here and pop out here. It should also want to expand and push against here and push against here. So we are told that in that shaded walls, they're physically attached to the red material. So the strain in the 1,1 must be equal to 0. So that's a fact. We're also pushing in, compressing the material in the 2,2 direction, so there will be a strain in the 2,2. And we also know that there is a stress in the 2,2 as well, and we could actually quantify that. There will be a stress in the 1,1 because the material should want to expand out here, but it's being prevented, so there will be a stress in the 1,1 as well. Is there a stress in the 3,3? Well, no, because the top is open, and so it's free to expand, so there will be no stress in the 3,3, but there will be a strain in the 3,3 as well. We also know the final length of the 3 direction, final length of the 2 direction, and we know it's a cube initially, so we could actually calculate, so we actually know and could calculate this and this. We can calculate this, so we have 3 unknowns here. Stress 1,1, Young's modulus, and Poisson's ratio. So let's get at this. So I'm going to close this. I'm going to open up a new, no more neural networks. It's for another class. Let's close the program. That is why you want to always save in Mathematica. So make sure to do so, if at all possible. So let's open up the screen, and then we'll get moving with this here. All right, so I want to go ahead and define some values. So actually, I know that, so my F22 is equal to minus 10 times 10 to the third. I want to make sure my units are all good to go. My L naught of my cube is going to be 10 millimeters, so equals 10 times 10 to the minus 3. I know that my sig22 is going to be equal to F22 divided by L naught squared. So we have that as well. I also know that my E22, my strain in the 22 is going to be equal to my final length, so 9.99795 minus my initial length, final length minus initial length over initial length. And we're also told that my length in the 3 direction, the final one is, so let's do E33 equals 1.00019. And these are all, ooh, be careful here. So our L naught, and actually let's do, so yeah, this is always y, 10 to the minus 3. So that's millimeters. This is centimeters. So times 10 to the minus 2 minus L naught divided by L naught. And we also know that alpha equals 1 times 10 to the minus 6. We're also told that my del t is equal to 100 minus 25. And now we can start to write out our equations. So for stress and strain. So we know that equation 1, my strain of the 1 is equal to 1 divided by y times sigma 1 minus nu times sig 22 plus sig 33, and then all of that plus alpha. I'm going to actually define that right now. My thermal strain is equal to alpha times del t, like that, et, phone home. That's my E1, and my E2 is the strain of the 22 times sig 22 times sig 11. And my 3 equation is going to be strain in the 3,3 and stress in the 3,3. And then instead of stress there, we're going to do that 1,1 here. And I can solve for all of these. Actually, excuse me, we need to also define that my E11 is equal to 0 and my sig 3,3 is equal to 0. And let's reevaluate. Boom, boom, boom. So now we can solve E1, E2, E3, and let's solve it for, actually we could probably just do that. So we know our nu has to be positive, and so we got that here. All right, so what material are we working with? Well, Poisson ratio of about 0.3, Young's modulus of about, what is that? Almost about, how many? Actually, that's quite interesting. It's about 2, basically gigapascals. So about 200, 300 gigapascals. So maybe metal, probably metal. So that's a possibility. Write out the full stress and strain tensor. We already calculated that. What are the principal stress values? So we are in, and actually I'm going to define it right now. Sigma 1 equals this. So we know, actually my maximum stress, because I actually have sig 22, sig 33. These are my principal stress values. So this is my largest principal stress, and then let's see, 1, 2, 3, basically 6. Yeah, so this is large. So it'd be sigma 1, sigma 2, sigma 3 would be right there. So those values. So I have those principal stress values. What about maximum shear stress? That is just going to be, actually I'll define it right now. So sig 1 equals sig 33. Sig 2 equals sig 11, because there's going to be exactly, and then sig 11, and then my sig 3 equals sig 22, and I'm going to find that my maximum shear stress would be sig 1 minus sig 3 divided by 2. That would be my value there. So that's going to be my maximum shear stress. So what about the rotation to get to maximum shear and principal stress? So I'm already in my principal stress state, so that rotation is going to be 0 degrees. To get to maximum shear, 45 degrees. Don't worry about that. If this material was actually the green material seen below, excuse me. So our green material has so my sig y is approximately, let's say, let's say 980 times 10 to the 9. Oh, I know, times 10 to the 6, excuse me. Here, so let's say is sig y greater than this. So, actually, if this is greater than, so this will not yield via, basically, I think that's Tresca. Rankine is just going to be sig 1, and then von Mises is square root of basically 1/2 times sig 1 minus sig 2 squared plus sig 2 minus sig 3 squared plus sig 3 minus sig 1 squared if this is greater than sig y. No yielding. So if this is the green material, we are not yielding. We will never yield. And that's it. So let's now get into some beam bending with problem 3. All right, we are back, and let's go ahead and start to solve. Actually, and my Mathematica is not. Problem 3. So let's pull this up, and actually I'm going to pull up our handy dandy, very, very cool beam bending Mathematica notebook, because we're going to solve this using ODEs, and we're going to identify essentially the problem. So PET is a polymer, so my Young's modulus, I'm going to say, is 1 times 10 to the 9th. We have our typical beam, and then look at our dimensions. So let's call L is equal to 100 times 10 to the minus 2. I am going to say that the thickness, so my height, is equal to 10 times 10 to the minus 3. My base is equal to 3.5 times 10 to the minus 2 here. So let's go ahead and get those. So with that defined, actually, sorry, we can now define our moment of inertia. So we're going to do I is equal to B times h cubed divided by 12. So we should get that here. I'm going to put parentheses just in case. Fantastic. All right. So we have our function. So we have a supported beam here. And actually, I'm going to go ahead and define my coordinate system. So y, x. I'm going to define this as x equals 0. And this is going to be x equals L. So we have a system here where I have I'm going to put it here. I'm going to put this another one. So I have a, pointing in the up direction, 10 times 10 to the 3. That is applied at a distance minus x L divided by 5. I'll bring this over here. And then I also have minus 1 Newton over x minus L, actually 3L divided by 4. So that's my function. So that's our Euler-Bernoulli beam bending problem. So that's a 4th order ODE I need for boundary conditions. So I know that at y of L, there's going to be no displacement because I have a support. So that is equal to 0. I also know that the slope at L will also be equal to 0. What's happening at that other end? That is a very good question. So what do we know about here? Well, there's no restoring moment, so we know that at this, the moment must be 0 at this location. What else do we know? What's the other thing that we can kind of solve in this problem? What else do we actually, or what else can we find? Well, shear. What else? What can we really do? So we know that we're pushing up here, right? We're pushing down here. What else do we know in this system? What can we say from our statics expressions to solve this problem? How can we deal with this? So we know here the displacement is 0. We know the slope is 0. Here, we know that there's no restoring moment. We also know that basically here that there will be basically a shear moment in here. But what else do we know? What do we know? What about the moment? Is there going to be a moment basically here? Yeah, right? We need the sum of the moments to be 0. So we're going to have basically some shear here, but there's also going to be some restoring moment, probably, because it's going to go like this, it's probably going to be in this direction here. So we could actually calculate that out and actually define essentially a moment in there. So my y, actually, and we could actually pull up and visit our old friend, our lecture notes. So we can actually pull up, where's our good mechanics? Let's do lecture 6, linear elasticity, just to kind of remind ourselves of our expressions that we have available to us. So let's go over here. Those are our transformations, but here we go. Beam bending. So we know, actually we can go ahead and scale that up just a little bit. We know that our moment here, and actually we can see here how we can relate moment is minus modulus second derivative. So we can calculate and set that moment. So let's go ahead and do that. So with this set up now, we could actually go ahead and calculate that moment explicitly. So let's go ahead and let's look at the moments. Actually, well, let's do the sum of the moments. So we have, actually we have to do the sum of the moments. Actually, yeah, let's do the sum of the moments around this origin here. So there will be basically what is that restoring moment there. So when we calculate that, and we can do that here, I'm going to have a moment around here. If we're pushing there, this is going to be basically clockwise. That's going to be clockwise. That will be clockwise, so it's negative, so minus 10 kilonewtons times, what's the distance? That's going to be 4L/5 from here to here. And then this will go counterclockwise plus 1 times L/4 right there. And then this will be basically, I assume that we're going to have to go against, so it's actually going to be minus my moment here, set it equal to 0. So let's go ahead and solve for that. So let's go ahead and knock that one out. So let's solve minus 10 times 10 to the 3 times 4L divided by 5, excuse me, plus 1 times L divided by 4 minus M set equal to 0. And let's look at this numerically. So we can say that that moment will be equal to this, so second derivative again, and those are my initial conditions. So I've got my initial conditions. I can now solve this here, and oops, let's see, what does it not like? So let's just do desolve. Interesting. What does it not like? I think this has to be at L, excuse me, because that's, and actually this, yeah, that has to be L, because it's the moment here. So let's go ahead, let's get that out. There we go. Let's get it over here. Let's set heavy side theta goes to 0. That's a good value here. And then, all right, so that's our solution. And so actually what we see here, actually something was a little bit off. So we actually, actually no, this works completely. So actually we need to plot it out to L. X from 0 to L. L is going to be basically 1 in this problem. Yeah. So makes sense. So we're pushing up. There's only a very small restoring force pushing down there, and we get our deflection. So that is going to be our deflection. So what is the maximum displacement, and where does that occur? So we can actually see, let's go over here. There's that maximum displacement value right there. So let's go ahead and, so we know where the maximum displacement occurs. It's going to occur here. We can see that on our solution, and actually we can actually use and actually extract a little bit. Where is it? So first, actually, before we even get to that, let's go ahead and let's calculate. So I also want to look at, for example, I may want to plot. So my moment equals, so my moment's going to be equal to minus y times I times derivative of sol with respect to x, x squared. There we go. Same thing for shear, except it's going to be to the third. So we can plot, basically, let's go ahead. Let's get that out here. Boom, 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 boom. Makes sense. 0 moment there until we hit that. What about shear? We've got that. We can see the plots there. We can actually, so for example, for sol, so find maximum value. Oops. Find max value of sol in the range of x from 0 to 1. Let's see. Find max value. Actually, let's look at the documentation. I think it's find maximum, actually. Let's look at this here. Yeah. So find maximum of our function, which would be sol from x from, let's see, I think you can specify the range. Basically here, like this. We can just specify like this. Let's go ahead and put it in here. And I don't want it to start anywhere. I just want this, and I want to look at my sol, and greater than 0, less than L. Is there a way we can just perhaps do this and this? It's not gonna work. I could just do this quite easily, but I want to do a little bit fancy. And I say let's just do starting x equals 0. And there you go. So that's the maximum displacement. So we are good to go there, and that's where it occurs. So we've got this. Will the beam yield? Well, to see if it's going to yield, we need to figure out our maximum stress value. And we know that value previously, and actually calculate it in our notes for stress. Our maximum stress will be maximum of our moment times y, which is half our thickness, over I. So let's go ahead and let's find. So if we look at our moment, we see that the moment is maximized at L. So let's do find minimum of our moment. And let's start at x at L. And we get this. So that's our moment. So stress is equal to minus our moment. And here divide our times h divided by 2, half thickness, all divided by I. So that is our stress. Now our stress tells us that our stress is positive. Does that make sense? So we're pushing up here, so our curvature looks like this. So if we look at this here, so our curvature is positive. So what's happening at the stress right at the top? Is it compression or tension? So that's actually compression, right? So we're compressed at the top and we're actually elongating at the bottom. And we actually picked the positive y/2. This has to do with kind of a change of notation. When you think about the moments, and especially we've defining, your definition of positive or negative moment, and considering that the beam is essentially going like this in the clockwise direction. So actually it should be negative, but it's the way the definition of the moment occurs. So this will actually be stress. The top of the beam should be a negative on top of that. So we actually have to change our definition of our moment. But again, you can kind of calculate that out and justify that. So calculate the maximum stress. It's going to occur here. We've got that. And then finally, will the beam yield? Well, it's PET, it's the black curve. So what is our stress here? I don't believe it will. Let's look at our stress. Ooh, actually, oh yeah, that will for sure, that definitely will yield. So there we go. Again, one of the important things to note is that change of notation. You can basically flip this to your negative moment. It's just a definition change. So it's just essentially the way that we define moments as being positive or negative, and that should match essentially with our intuition there as well. So positive curvature, positive moments, just follow essentially. Make sure to kind of confirm those answers with all those negatives, because the Euler-Bernoulli is different from probably what you've seen in statics and what we've kind of done in our class. All right, on to problem 4 in stents. All right, so now we're working with, again, another mystery material, stent, but it behaves like a polymer. So we know if it's polymer, Young's modulus is GPa, nu is equal to 0.4. Thickness is 10 micrometers, diameter is this. So let's go ahead and let's start to basically file these away. I'm going to quit the kernel, and let's quit. So my Young's modulus is equal to 1 times 10 to the 9th. My nu is equal to 0.4. My thickness equals 10 times 10 to the minus 6. And my radius is equal to 3 times 10 to the minus 3. If it's a thin wall pressure vessel, my R/T value must be greater than or equal to 10. Let's wait with bated breath. And we are definitely a thin wall pressure vessel. So with that, I don't know what the rest of the problem is going to say, but del P times R divided by T, sig L is equal to sig H divided by 2, EH is equal to 1 divided by Y, times sig H minus nu times sig L. EL is equal to 1 divided by Y times sig L minus nu times sig H. And we got that. All right. So the stent is actually the orange curve. They forgot to label the y-axis, but the values on the x-axis are correct. So if I'm looking at this orange curve, write out the full stress and strain tensors at the point of failure. So my material fails at a strain value of about, let's call it 0.24. I'm going to zoom in a little bit more. 2468. How is this supposed to go? Let's say 0.46. Not a huge deal. So my thin wall pressure vessel will always fail when my EH at my EH value. So EH, it will fail at a value of 0.46. So when it fails, my del P is this. So got that. Let's go back out and see what the question is actually asking us. Right at the full stress and strain tensors, well, once we found that value, I can do sig H, sig L, EH, EL, and that's my full stress and strain tensors. What's the pressure? We already solved for that. What's the value of maximum shear stress? So that will always be my sig H divided by 2 or sig L. So that will be my maximum value of shear stress. 3 principal stress values. my sig 1, for any thin wall pressure vessel, sig 1 is equal to sig H, sig 2 is equal to sig L, sig 3 is equal to 0. And we are in the principal stress strain. Excellent. That's it. So we are good to go. That was the orange curve, I believe. Just make sure that we did that right. Fantastic. All right. All right. So we are working with Sly Stallone on the classic movie Cliffhanger. So we're hanging on this side. We're hanging on the other side. We can approximate the yellow material as a ceramic. So Young's modulus is equal to 300 GPa. My nu is equal to 0.2. Attached to the blue walls seen here, the temperature has increased, so my delta T is 43, increased since the hanging 43. The force in the one direction, so my force in the one is minus, because we're compressive, 50 kilonewtons. And the final dimension of 3, in the 3 dimension, is 0.65. The force in the 3, which is extending, is 85 kilonewtons. Let's see. The cliff is attached to all the blue materials shown here. So we also know, so let's look at our stress and our strain tensors. So if we're attached, I know that the strain in the 2,2 must be 0. There is a change in the 3,3 because there's a change in the dimensionality. There will also likely be a strain in the 1,1 direction. If there's no strain in the 2,2, but obviously the material, there's a delta T and all those things, there should be a stress in the 2,2. There also will be a stress in the 1,1 and a stress in the 3,3. And if we look at this material, I'm hanging down like this. So again, what's my stress? Normal. And then what's the direction? We're going 3. So the positive face, I'm pointing in the negative direction. So that is actually a negative stress. And what is the stress? Well, the force is 100 kg times gravity, 9.8, divided by the area, which is effectively given here. So a lot going on in this problem. So let's start, and let's start by actually kind of writing everything out. So let's go ahead and quit the kernel again. I'm going to just start to kind of define some values. So I'm going to say that my Young's modulus is equal to 300 times 10 to the 9. I'm going to say that my nu is equal to 0.2. I'm going to say my F11 is equal to minus 50 times 10 to the 3. I'm going to say my F33 is equal to 85 times 10 to the 3. I'm going to say that my L01 is equal to 0.01. I'm going to say L02 is equal to 0.35. I'm going to say that my L03 is equal to 5 times 10 to the minus 3. Meters, good to go. Excellent. L03 is equal to, sorry, let me write that down. My final direction in the 3, L3 is equal to 6.5 times 10 to the minus 3. So we know that there is a strain in the 3 as well. And I don't know what my alpha is, but I know that my ET will be alpha times del T, and I know that my del T is equal to 43. What else do we know here? Whew, there's a lot. I know that my, for example, so I know my F11, so I know that my, for example, my sig11 will be equal to F11 divided by L02 times L03, because in the 1,1 direction, it's length 2 times length 3. I know that my sig33 is going to be equal to F33 divided by L01 times L02. I also know that my mass is equal to 100 kilograms, my G is equal to 9.8, and I know that my sig13 is equal to minus mass times G divided by, and if I look at that area, that will also be the L02 times L03, right here. Excellent. So, what are we to do? How can we solve the rest of this problem? what's going to happen? Well, let's just go ahead. Let's see what we've got essentially right now. So let's shift enter and evaluate this monster. And what do we know? What do we not know? And why is this giving me a number? Where have I not? Ah, here we go. So I don't know. And actually, we could actually calculate. There's a couple more that we can say. I know that E22 is equal to 0. I know that E33 is equal to L3 minus L naught 3 divided by L naught 3. So I know those two values. And then there's also going to be, sig 1,3, sig 1,3, epsilon 1,3, or excuse me, oops. Sig 1,3, sig 1,3. If there's that, it's going to be this. Everything else will be 0. Fantastic. So I have my sig 1,1, I have my sig 3,3. I don't know what my sig 2,2. So I don't know sig 2,2. So that's an unknown for me right now. I do know this because I have a very quick equation if I know my other values there. So I don't know this. I don't know what my, I believe I don't know what my strain in the 1,1 is, if I'm correct. And I believe that is true. So I don't know what this is. And and I don't know what alpha is. So I need 3 equations. I could actually calculate epsilon 1,3 right now, and we're going to go ahead and do that. So E13 is just equal to 1 divided by y times 1 plus nu times sig 1,3. So that's my epsilon 1,3, and again, that just comes from basically our expression that we've worked with previously. E1 is going to be equal to 1 over y times sig 1,1 minus nu times sig 2,2 plus sig 3,3. There's no epsilon t here because, again, shear stresses do not generate thermal expansion does not generate shear strains. So we got that one right here. Let's copy and paste. And then, oops, let's close that. And then, what don't you like? There we go. E2, let's go ahead and let's copy this. Normal stresses, yes, I do need to actually take care of that one. This, and then E11 set equal to this. E22 set equal to this. This is going to be sig 2,2, and this will be sig 1,1. And then finally, E33, 3, sig 3,3, sig 2,2. And then let's solve E1, E2, E3 for my unknowns. And we've got it. That's it. So, full stress and strain tensors, got it. Oops, got it. What is the rotation to principal stress? This is a trickier one. So, if I look at my stress tensor, if I look at this plane, if I look at the 1,2 plane, I'm in principal stress. If I look at the 2,3 plane, I am in principal stress. But if I don't have those, now here's where I'm going to have to pull out the big guns and do our little more circle transformations. So I'm going to download, actually I'm going to open this right here. So I'm not going to use plug and chug, I'm going to use my linear algebra approach. And so I'm going to define right here, let's go back over here, let's define this. Sig 2,2 is equal to this now. So here. So my sig 1, my plane, sig 1,3 plane equals, I'm going to have sig 1,1, sig 3,3, sig 1,3. So that's the plane. So I need to solve what's the angle. So I need to do t dot sig 1,3 plane. And I want to pull out the third equation. And I want to solve when does this equal 0, because I want that new shear stress value to be 0 in terms of theta. Let's And there we go. That's it. That's the values. So it could be this, could be this. We're pretty close. So that will be your rotation, essentially, to get there. That's rotation to principal stress. What values? We can actually do that right now. So the values would be, if I take this, and if I do t dot sig 13 plane slash dot theta, theta goes to this, we can see that basically this is 0. This would be my sigma 1. This would be my sigma 2 value, or those normal stress values. Excellent. If I'm here, if I want my maximum shear stress, I can just do plus 45 degrees. Let's take this. Sorry. And voila. This would be my maximum shear stress value. So I can find those as well. Excellent. Done and done. Now, finally, I weigh approximately 100 kilograms, and I'm standing on a polymeric material, so I have a rigid box. It's a polymer, 15 millimeters. So rigid box, polymer, so Y is equal to 1 GPa. Nu is equal to 0.4. I'm standing here, 100 kilograms. Dimensions. What temperature do I need to reach to ensure that when I step on the cube, my position on the box does not change? So if I'm looking at dimensions like this, so I have my material properties, my dimensions, what about my stresses? Well, when I sit on the box or stand on the box, I'm going to generate a stress in the 3-3 because it should be compressing, and then it's going to push out here and here, so there's going to be stress everywhere. Additionally, I'm going to assume it's well lubricated. Now, if I am confined here and it's pushing out, there's going to be no strain here, there's no strain here, but there will be a strain in the 3-3. But we actually have to figure out what's my delta T to make sure that this is also 0, that this does not change. And we'll know this value as well. So, what can we do? How can we solve this problem? Well, let's set it up just like we usually do. So I'm going to quit everything here. So, and then let's also, if we look back at our notes, and especially at our linear elastic approach, for polymers we can do one more trick since we know it's the material, because it's an unknown that we need to solve for. Let's see, where are you? There's. So for polymers, typically, let's say it's 500. Let's say it's a pretty normal polymer. Let's say 50 times 10 to the minus 6 is my alpha. So my Y is equal to 1 times 10 to the 9th. Let's say my nu is equal to 0.4. Let's say my alpha is equal to 50 times 10 to the minus 6. Let's see, my del T is an unknown. So my ET is equal to alpha times del alpha times del T. I know that my sig 3-3 is equal to minus 100 times G 9.8 divided by 15 times 10 to the minus 3 squared. I'm going to just button that up. And I know that my sig 1-1 exists, but I know that my E11 is 0, my E22 is going to be 0, my E33 will exist. So let's get cracking. So E1 is going to be equal to 1 divided by, I'm going to actually copy over here. Sometimes it'd be very nice to have this in your back pocket. Here we go. So we've got this, and then we want actually E33, we're solving for when this will be equal to 0 as well. So boom, 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 and we can see in here sigma 1, sig 2, del T. Let's solve it. E1, E2, E3. Voila. Shockingly, you only need 17 degrees to lift, or to basically prevent me from compressing that material. So that is it. P-set 6, the monster of a P-set, is done with. So again, study well, and I'll see you in the next video. Thanks. Bye.